So scientific measurements are recorded in a specific way. We record a measurement so that every digit is certain except for the last digit. The last digit in any experimental measurement, scientific measurement, is estimated because we cannot measure things exactly. You can't say that this piece of paper is exactly 11 inches long, because if you could zoom in, you'd see not quite, right? So there's uncertainty in every measurement. This is just an example from your textbook showing levels of carbon monoxide in Los Angeles County. Here they're expressed with 1 decimal point, so 2 significant figures, 9.9 parts per million, 9, 7.4, 2.8, 1.9, 1.1. Over here they're expressed to the ones place. So here, when it says 10 parts per million, we assume that there's uncertainty in the last digit, which is the 0. So when I see 10 parts per million, I think, well, that's between 9 and 11, somewhere in there. This one, 9.9, though, the uncertainty is in the tenths place. That's between 9.8 and 10.0. That's a more precise measurement. So scientific measurements, the last digit is estimated. So let's look at how we would do that. And this is something that will come up in lab. It's not something that we do naturally in everyday life. We need to turn this on in science class. So how many digits you record depends on what you're using to measure the thing. So there are analog devices and there are digital devices. Digital devices are no problem. They actually, like a digital watch, they just show you numbers. Our balances are digital. You just write down all the numbers. Easy peasy. The hard thing is with what are called analog devices, and we have a lot of those that we use in lab. So here, this is a little kitchen scale. It's got ounces and grams, so the English system and the metric system. This is chemistry class. We're always going to look at metric if it's available. So we're looking over here. So we've got a pistachio sitting on this balance, and we're trying to figure out how much it weighs. Well, how many digits we record depends on the instrument. And so one way to help you remember what to do is remember to read between the lines. So we're looking at these smallest divisions. There's a 0 here, and this is 10 grams. So each of these lines represents 1 gram, right? So when we look at this line here, it's between 1 gram and 2 grams. So it's 1 point something. Is there any uncertainty in the 1? No. There are literally lines there. It's between the lines. It's 1 point something. So we don't want to just say, well, it's 1 gram, because it's clearly between 1 and 2. We're going to write 1 point something. We have to estimate. So in your brain, you look at the division, the space in between there, and you kind of just estimate divided into tenths. And so you can see, well, it's definitely less than halfway, right? So now we've got it narrowed down to between 1 gram and 1.5 grams. But we have to put a digit in there. And so you estimate. So we might estimate this as being 1.2 grams. Well, I think it's 2/10 of the way from the one line to the next line. Now, someone else might look at it and say, well, I think it's 1.3 grams. You're both right. Okay? It's an uncertain digit. It's subject to interpretation, right? But we include it. Yes?
How far can we go on those estimates?
So you can go 1 decimal place past the smallest division. So we look at these lines, each of them is 1 gram. So 1 gram we can measure with certainty, so we can measure tenths by estimation. Past that, it's ridiculous, doesn't mean anything at all. So on a ruler, rulers have centimeters, And the individual small lines on there are tenths of centimeters. So we want to read between the lines. So the lines represent a tenth of a centimeter. That means that we're going to estimate the next decimal place, the hundredths place. On a thermometer, a lot of the thermometers have 1 degree markings. We're going to read between the lines. We're going to move to the next decimal place and estimate tenths. Any questions? So let's practice. So here's a thermometer. This is in degrees Celsius, and they didn't do a real great job of taking this picture because you can barely see where the red level is. It's right there. So let's decide how many digits should we have here. What does each of these individual lines represent? 1 degree, right? So that means we're going to estimate the tenths degree. So we look at this and we see that it looks to be here. So this is 100. So it's 103, maybe a little bit higher. So we're going to write 103. There is no uncertainty in the 3. We've got a line. We're going to estimate the next decimal place, which is the tenths place. So we're going to estimate. Well, what do you think? Maybe 0.1? It looks like maybe it's a smidge past. So 103.1 degrees Celsius. Somebody else might say 103.2 degrees Celsius. It's all okay. There's uncertainty. Yes?
If I thought it looked like 0, is that incorrect to put?
No, that's okay. So you might say, well, no, it looks to me like it's right on the line. So 103. I think it's just right there, 103. I still have to write the next decimal place. So I'm going to write 103.0 degrees Celsius. Okay? The 0.0 there is really important, and that's the one that students often leave off. 103.0 versus 103, that's a significant difference in how closely was that measured, because if I see 103, I interpret that as between 102 and 104. There's uncertainty in the last digit. That's this big range. When actually we measured it on this thermometer and it was within a tenth of 103. So very, very close to 103. You see the difference? So it's very important to record the correct number of digits. As you do experiments and make measurements, you'll probably wonder, am I doing this right? Do I have enough? Do I have too many? Ask me, okay? I'll talk to you about it, and eventually the pattern of reading between the lines, 1 digit, 1 decimal place past, will click, and then it's easy to remember. But you have to kind of work through that a few times. Let's look at this graduated cylinder over here. So this curvature here is called a meniscus. And we'll learn in a later chapter that that has to do with adhesive and cohesive factors and surface tension and all sorts of stuff like that. But for now, we just say, well, that's what it is. The surface of the water curves. So if you measure the bottom of this or the top of this, that's going to give you a different volume. So scientific glassware is calibrated to be measured to the bottom of the meniscus. So we're always going to look for the bottom of this. So we look at this graduated cylinder. These are in milliliters. We zoomed in too much so you can't see that. So this is 4 milliliters. That's 5 milliliters. What does each of these lines represent? 0.1, right? So that means we're going to estimate to 0.01. So the line, each line is 0.1 milliliters. So we're going to estimate to 0.01 milliliters. So here's the bottom of the meniscus. It's between 4 and 5. There's the 4, and this is 0.5. So we've got 4.5 There is no uncertainty in the 5. It's a little bit above that, but it's definitely less than 6. It's 4.5 something. And then we're going to estimate that last digit. What do you think? Maybe 8? 4.58 milliliters? 4.57? There's several different possibilities. I think it's clearly above 4.55, but beyond that, it's an estimate. Okay? And I will get on you in lab about this because it is important. Exactly what that last digit is, exactly what you record there isn't so significant, but just the fact that you record the digit, that's what's important. Any questions? Okay, significant figures. You all heard of significant figures before? Okay. So hopefully this will be review. My guess is that they were a bit mysterious in your previous chemistry class. And so hopefully when I explain them to you today, it'll kind of click and you'll go, oh, that's what they meant by that. So this seems like a torture device that we've created for students just to make your life miserable. That's actually not the case. The alternative to significant figures is differential calculus. Error analysis, very long, very tedious, gives you a better result, but teaching that is like, ugh. If you're a chemistry major and you take physical chemistry, you'll learn about that then in a couple years. So this is actually a simpler method of keeping track of the uncertainty in a measurement. Anytime we make a measurement, there's some uncertainty. When we do calculations with those measurements, we can end up with a ridiculous number of digits like we saw in some of those earlier examples. And so significant figures tells us how we should round those, what's a reasonable number. So what we mean by a significant figure, sometimes called a significant digit, these significant digits, significant figures are all of the certain digits and that one estimated digit. Okay, so that example we just did with the thermometer and the graduated cylinder, when we make a measurement like that, all of the numbers that we write down are significant figures because we write down all the ones that we're certain of and we write down one uncertain digit. The more digits you have, the greater the certainty or the precision of the number. So we need to be able to look at a number and identify what are the significant figures. Which of these digits are significant? And it's the zeros that cause problems. Any digit that's not a zero is going to be a significant digit. And so here we have examples, the 1, the 3, and the 1. The 0 is not a non-zero digit. Over here we've got 3 digits, the 4, 2, 1. Non-zero digits, you always count those. So it's the zeros that cause problems. There are 3 kinds of zeros. There's zeros in the middle of a number, there's zeros at the beginning of the number, and there's zeros at the end of the number. So interior zeros, these are ones that are between non-zero digits, you always count those. Leading zeros come at the beginning of the number. I made this extra large. Leading zeros are not significant. They are there to hold decimal place. If I took this number 0.00023 and I got rid of the zeros, I'd have 23 or 0.23. And that's not the same value, right? But these zeros at the beginning do not reflect measurement. They are just important to locate the decimal point. So zeros at the beginning of the number, you never count those as significant figures. Zeros in the middle, sandwiched between non-zero digits, you always count those. And so then that leaves us with the last one, the trailing zeros, the zeros at the end of the number. And sometimes they are, and sometimes they aren't. Okay? The explanation that I'm going to give you here is a little bit different than how the text explains it. both methods will get you the same answer. So if you don't like my method, you can use the book's method. It'll also get you the correct answer. So the way I think about this is trailing zeros, we're going to count them or not depending on whether there's an actual decimal point written in the number. So in this number, 39.0, obviously that 0 is not necessary to hold a decimal place, and so that's going to be counted. In this number down here, 300, there's no decimal place. If I didn't have, there's no decimal point. If I didn't have these zeros, it would look like a 3, right? I have to have those zeros to locate the decimal point. Zeros that are there just to locate decimal points are not significant digits. They're just placeholders. So if I have a written decimal point, I don't need the zeros to locate it, and so then any zeros that are present at the end of the number are going to get counted. Now this number here, 1.432000. Those are not needed to locate the decimal point. Those are there because they were measured. And the first two are certain, and the last digit's always uncertain, and so we're going to count all of those as significant figures. 29.310. There's a written decimal point, count all the trailing zeros. Here we have no written decimal point. There's an implied decimal point. If I said put a decimal point on that number, you would know where to put it, right? But it's not actually written. So these zeros are ambiguous. We can't really tell. Do they mean that it's 300 to the nearest one and there's uncertainty in the ones place? Or is there uncertainty in the hundreds place? The way it's written, we can't tell. It's ambiguous. So unfortunately, this happens a lot. And so when we see something like this that's ambiguous, we want to assume the worst. Okay? Assume worst case scenario, it's not significant. But the best answer is those zeros are ambiguous. So we should avoid them. We can avoid those sorts of zeros using scientific notation. So 300 could be written as 3 times 10 to the 2. The times 10 to the 2 takes care of the holding the decimal place, right? And now I just have that 3, and I can clearly see, okay, the uncertainty is in the last digit, the 3. 238,100 in scientific notation would be 2.381 times 10 to the 1, 2, 3, 4, 5. So I am not going to specifically teach you scientific notation because you should have learned that. And I know some of you are a little rusty on it, so ask me in lab. Quick refresher here. What you're going to do to put a number in scientific notation is you move the decimal point from where it is or where it's implied so that it's after the first non-zero digit. So I'm going to get 2.381. Yes?
So if you were trying to show 300 with a significant digit, so we put it as 3 times 0, so it should be 2.
Yes. If I wanted to indicate that those zeros were significant, I'd write 3.00 times 10 to the 2, and then it would be clear. So you move the decimal point so that it's after the first non-zero digit. So you always have one digit and a decimal point, and then sometimes you don't have anything else. Sometimes you have a whole bunch of other stuff. And then you count how many places did I move the decimal point from where it was originally. So it should have been here, and I moved it 1, 2, 3, 4, 5 places. So the exponent is 5. And then sometimes it's hard to remember, should that be a positive 5 or a negative 5? So guess, how do I feel, positive or negative, about large paychecks? I feel positive about large paychecks. And how do I feel about small paychecks? I feel negative, right? So is this a big number, 238,100? It's a big number, like a big paycheck. I feel positive. It has a positive exponent. This number up here we could put into scientific notation. Again, we're going to move the decimal point so it's after the first non-zero digit. So there's some zeros at the beginning. We just ignore those. 4 is the first non-zero digit. Put the decimal point after that and then write down the other stuff. Times 10 to the, and then I'm going to go, I moved it 1, 2, 3 places. So the exponent is 3, negative, because that's a small number. I have negative feelings about small paychecks. It's a negative exponent for a small number, positive exponent for a big number. Okay? Any questions? Then we have exact numbers. So exact numbers have no uncertainty. How many pencils am I holding up? 2. Is there any uncertainty in that? No, that's exactly 2 pencils. It's not 2.005 or anything like that. It's exact because you can count them. They are discrete objects that you can count. Okay, so there's no uncertainty. That would be exact. If I'm going to use a number like 2 pencils in a calculation, that is not going to contribute to any error or uncertainty in the end result. And so we just don't even have to consider it. Another way to think of it is we could say that it has an infinite number of significant figures. So I could write 2.0000000. I could just say 0 the rest of the day. And that would be true because it's exact. So counting of discrete objects. What about 2 inches? Is an inch an object? No, you can't count the object. It's a measurement. It's a unit of measurement. And so when we see something like 2 inches, we see, oh, whole number must be exact number. No, it has to be something that you're counting. Other things are integral numbers, meaning integers, whole numbers, that are part of an equation. So the diameter of a circle is equal to 2 times the radius. That's an integer in the equation. It's defined that way. So that number is an exact number. Then we also have defined quantities, and these are often conversion factors between units. So 1 gallon equals 4 quarts. In the English system, it's defined that way. If you measure a gallon of stuff, there's going to be some uncertainty. But if you're looking at the relationship, a gallon is exactly the same as 4 quarts. So those are examples of exact numbers. Some conversion factors are defined quantities. They're exact. Others are not. How do you tell? Well, look at the 2 units. Here, gallon and quart are both in the English system. They're in the same system, so their relationship is defined. Liters and milliliters are both in the metric system. Their relationship is defined. When you go between metric and English, then usually it's not an exact number. There's a couple of exceptions. The inch centimeter one is an exception. Shoot. Okay, so let's practice counting sig figs. So here we have a distance measurement, 554 kilometers. How many significant figures? 3. There aren't any zeros there, so that one's a little bit easier. There's 3 non-zero digits. There we go. Okay, letter B, 7 pennies. That's an exact number, okay? Because you can count 7 pennies and there's no uncertainty. So the question is asking how many significant figures? Infinite. There's an infinite number of significant figures. Like if you're doing mastering chemistry, it might want you to say infinite on a worksheet, infinite or exact. There's a worksheet we're going to do in class today. You could write the infinity symbol or you could write exact. Either one is fine. 1.01 times 10 to the 5th meters. 3. So in scientific notation, any zeros that you see here before the times sign are going to be significant. This is an example of an interior zero. You might have a trailing zero with a written decimal point, but you'll never have leading zeros. You'll never have trailing zeros without a decimal point. So scientific notation, just all the digits before the times sign. The times 10 to the fifth is the placeholder part. So this is 3 sig figs. 0.00099 seconds. 2. Because leading zeros don't count, they're holding a decimal place. 1.4500 kilometers. 5. We have trailing zeros here, but there's a written decimal point. It doesn't matter where the decimal point is in the number. A decimal point written down means any of the zeros at the end are going to be counted. 21,000 meters. 2. If pressed for a number, you'd say 2 significant figures. A better answer would be, that's ambiguous. Because we can't be sure what the writer of that number meant. They might have meant 21,000 meters to the nearest meter, or to the nearest 10 meters, or to the nearest 100 meters, or to the nearest 1,000 meters. We can't tell. So then, if we're pressed to give a number, we'll say 2. Any questions? So when we do calculations, the result of the calculation should reflect the precision of the measurements that went into that calculation. You can't gain or lose precision just by doing math on a number. You can't estimate that something's a foot long and divide that into thirds and say, well, this piece is 0.33333333333 feet, right? You don't know that. So we're not going to gain or lose precision. So there's 2 categories of operations. There's multiplication, division, and there's addition, subtraction. And there are different types of operations, and so they have a different sort of rule. So we'll start with the easier one and the more common one. When you're multiplying or dividing, your answer is going to have the same number of significant figures as the one with the fewest sig figs. So when we're multiplying these numbers, these are called factors. This factor and this factor and that factor. Multiply them together. So you do the math on your calculator and write down more digits than you think you're going to need. And then we're going to go back and look at, well, how many sig figs did that number have? It's got 4. 1.052, this has 4 sig figs, and this one has 5, and this one only has 3.
2.
Sorry, 2, yes. I can't even read today. I was looking at this 3. It says 2 significant figures, as it says right here. And so then the easy part is, well, what's the smallest? 2, 4, or 5? Well, 2 is smaller. So I'm going to cut this off at 2 significant digits. So the 6 and the 7. And we'll go over rounding in a minute. But a good practice is write down more digits than you think you need from what your calculator showed you, and then figure out how many significant figures and go down and underline the last significant figure. The next digit is going to tell you whether you round up or down. So this one, the next digit is 2, and so I'm going to round to 6.7 because this number is closer to 6.7 than to 6.8. Here's another one. We've got one number divided by another, and we write down what the calculator is showing us. This one has 5, and this one has 3 significant figures. So the answer will be limited to 3 significant figures. So the leading 0 doesn't count. I've got 626. This is my 3rd digit. I look at the next digit, a 0, so I'm going to round down, and I get 0.626. Any questions? So adding, subtracting is a little different. We're looking at the answer has the same number of decimal places as the quantity with the fewest decimal places. Okay, So there's a couple of different ways you can look at this. One way is to stack them up like you were going to do this without a calculator. Use the calculator to get the answer, but then stack them up and pretend that you didn't. So stacking them up, all the decimal points have to line up. And then you're going to look for which of these numbers ends first. The 0.07 ends after the second decimal place. So I can draw a vertical line here, and that's going to tell me that my answer is going to end after the second decimal place. Another way you can think about that is think about, well, what's the uncertain digit in each of these numbers? It's the last digit, right? So this is uncertain in the first number, and the 7 is uncertain in the second number, and this last 5 is uncertain. When I'm adding these together, I'm going to add this 5 to what's there? We don't even know. And up there, what's there? We don't know. So how do you get a 5 at the bottom? Well, we're assuming that the other things are 0, right? So I took this 5 that I wasn't sure about, and I added it to assumed zeros. Is there uncertainty in that 5? Heck yeah. The next place over, when I add, I've got 5 plus an assumed 0 plus 7 is going to give me 12. Is there uncertainty in the 2? Yeah, because there's uncertainty in this 5. I'm adding a 5 that I'm not sure about to a 7 and a 0 assumed. So that's uncertain. The next column over, 4 plus 7 plus 9, and the 10 we carried from the previous one, I'm going to end up with, what, 21? No, 11. Wait, what? Yeah, 21. That's a 9 out of, I don't know. This is why you use your calculator. We should be able to do this, but we don't always successfully do it. There's no uncertainty in the 4. There's no uncertainty in the 9. But there's uncertainty in the 7. So then in the sum of those numbers, there is uncertainty in that 1. In the next place, there's no uncertainty in the 3. Now this is not a significant figure, but is there any uncertainty there? No, we know that's 0. And the 9, no uncertainty. So when I add those, this 4 doesn't have any uncertainty. And as I go further to the left, none of those have uncertainty. What we do is we keep all of the certain digits in the first uncertain digit. So where does that end up being? Right there. So I'm going to keep this digit because it's uncertain, and I just want one of those. And so then I'm going to report this as 5.41. It's a different way of thinking about that same process. And I can explain that several other ways for you as well. So if you are a little fuzzy on that, ask me in lab. Rules for rounding. You're going to look at the first digit that you're getting rid of. So you identify the last digit that you're keeping, and then you look to the next one. If it's 4 or less, 0, 1, 2, 3, 4, you round down. If it's 5, 6, 7, 8, 9, you round up. Okay? It is very important that you not change the magnitude of the number when you round it. And this tends to happen when you're rounding large numbers and you're rounding to a place that's in the tens, hundreds, thousands. So just as an example here, let's round $24,938.99 to 3 significant figures. Well, we don't have any leading zeros, so I've got 2, 4, and 9. There's my third significant figure. I'm going to look at the next digit to see, do I round up or do I round down? I round down. So is this $249? No. It's $24,900. We can't change the magnitude, the overall size of the number, just by rounding it. But students often, I don't know, you checked your common sense at the door, and I'll see people round that and say, oh, it's 249. Well, I'll do some business transactions with you, and I'll make a heck of a lot of money off of you. Question?
If you're going down, do you have to always put 0?
So that's a good question. It depends on what decimal place you're rounding. So here I'm rounding in the hundreds place. And so I have to fill in until the decimal point with zeros. A better way is to put it in scientific notation, and then we don't have to worry about it. So if I take this number and I put it into scientific notation, I can round it actually as I do that. So I would put the decimal point after the 2, 2.49. There's my 3 digits I want to keep. And I look at the next one, I'm rounding down, so I'm just going to drop it, times 10 to the something. Decimal point was here. I moved it 1, 2, 3, 4 places. So number 4 there, positive or negative? Positive. I'd like a paycheck that was $24,938.99, right? For a month, that'd be great. I don't get that. So there I rounded it to 3 significant figures. I didn't have to put in any ambiguous placeholding zeros. If you're rounding in the ones place, you won't need any placeholding zeros. The tenths, hundredths, anything to the right of the decimal place, no problem. It's when you get into the tens, hundreds, thousands, then you have to fill in with zeros. Otherwise, you're changing the size of the number. So 5.37, round it to 2 significant figures. So I'm keeping the 5.3. I look at the next digit, it's 7, so I round up, that's 5.4. It's closer to 5.4 than it is to 5.3. You did this sort of stuff on a number line in elementary school. You know, you wrote it all. Is this closer to 200 or 300? Right? It's the same idea. It just seems scary because it's in chemistry class, and it makes it worse somehow. 5.34. Well, I'm keeping the 5.3. The next digit's a 4. 4 or less rounds down, meaning I just knock them off, it's 5.3. 5.35. If the first digit I'm getting rid of is a 5, I round up, so that's 5.4. 5.349. Okay, I don't look at the 9 at all. Occasionally I'll get students, they get a little overzealous and they're going to start all the way at the end and round backwards up to where they need to stop. Don't. That's a waste of time and sometimes gives you the wrong answer. All I have to do is look at the 4. The 4 tells me to round down. That's 5.3. Okay? So we do a calculation, we identify the sig figs, and we round the number. If we're going to take that number and do more calculations on it, we don't want to round it just yet. Because if we round at every step, we're going to introduce extra error into our calculations, and that's not what we want. So to avoid rounding errors, we only round the final answer. We don't round the intermediate steps. So sometimes you're doing calculations and you're writing down intermediate steps. Sometimes you have to, sometimes you just feel better doing it that way. So my advice is here. Carry at least 2 extra digits. Too many digits is always better than not enough, because you can knock them off later. Carrying too many digits will not cause any rounding errors. Carrying too few will cause rounding errors. So what I have found works very well is if you have to write down an intermediate value, write down 2 extra digits You don't even have to worry about rounding those. And then carry on. And at the end, you can round your final answer, and you won't get any rounding errors. So an example here, you've got multiplication and subtraction. And so those are two different types of operations. They have different rules. So we have to look at the subtraction. When I subtract these numbers, my calculator gives me 0.479. But this number had 3 decimal places, and this only has 2 decimal places. So the result of the subtraction has uncertainty in the second decimal place. So I'm going to write this number down, and I'm going to underline the 7. I'm not going to round it up to 0.48. I'm going to write 0.479 and just underline the 7. That tells me, okay, that's the last sig fig there. Then I'm going to multiply. I've got this number and this number and this number, and I multiply, and the calculator gives me something like this. And then I have to look, well, this has 3 sig figs, and this one has 4 significant figures. And how many significant figures does that number have? It looks like it has 3, but I underlined the 7 because that's where I would round it, so it only has 2. So that tells me I'm going to round my answer to 2 significant figures. If you round this to 0.48, that can change the end result. Sometimes it ends up rounding the same, but sometimes it doesn't. So let's do some examples here. So this first one is all multiplying and dividing. So we can just do this all together on the calculator and use the one rule. So the first thing I'm going to do is I'm just going to do the numbers in the calculator. 3.1007 times 9.441 times 0.0301 divided by 2.313 equals. And my calculator is giving me a lot of digits. Personally, I don't like writing down all those digits. So instead of writing all of them down, you can write all of them down. That is absolutely fine. But I know a lot of you don't feel like it. So I've got the number in my calculator. I'm going to look at what I've multiplied and divided and figure out how many significant figures is my answer going to have. 3. This one has a whole bunch. This one has 4. Here, leading zeros don't count. That's 3 significant figures and 4. So my answer is going to have 3 significant figures. So what I'm going to do here is I'm going to write down the first 3 significant figures, and then I'm going to write down 2 extras. So I've got 0 point, that one doesn't count, 380. There's my 3 sig figs. And then I'm just going to write down the next 2 digits, 87. That 7, I don't even have to worry about rounding, just write it down. Now I'm going to look at this number and round it for my final answer. So what should the final answer be? 0.381. The reason I want to write this down first is we don't always know when we're going to need to use a number in the future, especially in lab. You're doing calculations and you find out, oh shoot, I needed more digits because I don't want to use this rounded number in a future calculation. Here I wrote down 2 extras, which is not that hard. And then if I need to use this in a calculation, I can just take this and use it, and I don't have to redo the calculation. Let's do this next one. So again, just do it on the calculator. Oops. And if you have a calculator that shows you what you've typed in, that can be really helpful because you can go back and look, do my numbers match? Because I just screwed up a little bit. I had 1,332.1. But I could see that, and so I fixed it right away. Equals, and my calculator is saying 104.3601. I could write all of that down. Or I can think about it and say, well, adding and subtracting, I'm looking at the fewest number of decimal places. Bless you. This one has 3 decimal places, 1 decimal place, 2 decimal places. So my answer is going to have 1 decimal place. So as I write down my unrounded number, I'm going to keep 1 decimal place. I'm going to underline that because that's my last significant figure. And then I'm just going to write down the next 2 digits, 6 and 0. Then I'm going to say equals, and now I'm going to round it and call it 104. What did I do? Oh, I multiplied.
I did it 3 times, I got 120.
Yeah, I did it wrong. I multiplied instead of adding. Thank you for catching that. Because it's really sad when, a week later, someone on YouTube says, "How did you do that?" And I realize, oh man, I did it wrong. Okay. Oops. So 1, 2, 0. Is this looking better? Yeah. I screw up all the time. I'm human. Okay. So the 9 is the 1 decimal place, and then the next 2 digits I'm going to write down. If there aren't 2 more digits, you don't have to write them down. But so there we go. Now when I round this 6 tells me I need to round the 9 to a 10, right? So that rounds this 0 up to a 1. So should I write 121?
No, 0.
It needs to be 0.0. I still need 1 decimal place. Okay? And that's a common thing that'll happen is people forget that 0. It is super easy to make a mistake when you punch numbers into your calculator. So I have the best 2 out of 3 rule. If I care about the answer being correct, I'll do it twice. If I get the same answer both times, either I'm really good at making consistent random errors or I did it correctly. If I do it twice and I get 2 different answers, I'm going to do it a 3rd time. And hopefully that'll match one of the first 2 and we'll go with that one. So in class, I only do it once and I depend on you guys to be the second one. So there you caught my mistake. Okay, letter C. Now we have multiplying and dividing, and we have adding. And so we have to look at them separately. You can do this calculation on your calculator with parentheses and come up with an answer and write it down. But you're still going to have to go back and do the pieces to find out the sig figs. So we'll just start that way. Here we're going to do the adding first. So 44.11 plus 1.223 equals. So that result is 45.333. If that was the end, what would the last sig fig be? Yeah, the second to the last 3, this second decimal place. I'm adding, so I'm looking at decimal places, 2 decimal places, 3 decimal places, right? So this is my last significant figure, the uncertain one. I'm going to keep the other 3 there because I don't want to round it just yet. So now I'm going to take this number times that number and divide it by this number. 2.511 times 21.2 divided by 45.333. Now I've got all multiplying and dividing, so I'm looking at number of decimal places. Number of significant figures. So 1, 2, 3, 4, 5 sig figs, right? And 4 sig figs. And here, we're not looking at all the digits I wrote down. We're just looking up to the underlined one. So that's 4 sig figs. So my answer should have 4 significant figures. So as I write it down from my calculator, I've got 1.174. There's my 4th digit. I'm going to underline it and write down the next 2 digits. And then I'm going to round that. It's going to be 1.174. Okay? This one, we have multiplying in parentheses, and then we're going to add the 4.811. So I need to look at the result of the multiplication and identify how many significant figures and where is the last significant figure before I add it. So 12.01 times 0.3. So the calculator gives me 3.603. But how many sig figs should that result have? Just one, right? This one had 4, but leading 0 doesn't count. The 0.3 only has one significant figure. So the result of this only has one significant figure. That is the uncertain digit. Now I'm going to do my adding. I'm going to take the number. It's in my calculator. I don't do anything to it, and I add 4.811. And my calculator is showing me 8.414. I was adding this number where the uncertainty was in the ones place to this number where the uncertainty is in the thousandths place. So my answer has to end in the ones place. And so this is going to get rounded to 8. Any questions? Yeah, so when we're adding, we're looking at decimal places. And so we see, well, we have the second decimal place. The reason it's important to write this down and underline it is because then I'm using a different rule for multiplying and dividing. And I can't just look at, oh, well, this one had 2 decimal places, because that doesn't help me when I'm doing multiplying and dividing. When you're adding and subtracting, you can end up with way more significant figures or way fewer significant figures than the smallest one. And so you really just have to write it down. One way to use the lecture videos is to go back and do these examples at home. So you get to the beginning of this slide where I haven't started doing the first problem, and you do it yourself without looking at your notes. And then you watch a little bit of the video. Did I come up with the same number? Oh, cool. Or you're doing the problem and you're like, I don't even know what to do next. Well, watch a little bit more until you're like, oh, I know it now. Pause it again, finish on your own. Okay, so you can use that to help yourself. Okay, so we talk about accuracy and precision. Accuracy is how close to the true value is what is the thing that you measured. And precision is referring to a series of measurements. How close, are those measurements to each other? So here we have some data from 3 students, and what they did is they took a block of lead and they weighed it on the balance and they record their measurements. And so we can look at these numbers in a table, and it's kind of hard to get anything out of it. That's why scientists use graphs. So if we graph it, it's easier to see what's going on here. So student A, there are the 4 measurements, and this one was really high, and that one's really low, and then, it's just all over the place. And there's a lot of variation in the size of the measurement. That means these measurements are not precise. They're scattered all over the place. To measure the accuracy, we're going to take the average of all the measurements and see how close it is. So here, the average is 10.13. The true value is 10.00. The uncertainty should be in that second decimal place. So 10.13, not good. So not precise, not accurate. Student B, all of these columns, all the measurements are really close to each other, right? Very consistent. So these measurements are precise, very consistent. But then we look at the average is 9.79. That's a lot smaller than the true value. So you can be you can be precise, but not accurate. What you hope to happen is that you're accurate and precise. So here, all the measurements are close to each other, and the average is very close to the true value. So this average has uncertainty in the second decimal place. And so that agrees very well with 10.00, also uncertainty in the second decimal place. It's also possible to be accurate and not precise. There are two kinds of error. There's random error and systematic error. We always have random error. Random error is it might be too high, it might be too low. There's an equal probability of it being too high or too low. We can get rid of random error by making repeated measurements of the same thing. Some are too high, some are too low, but then when we take the average, the random error is going to go away. So we can get around that. Systematic error is going to tend either to be too high or too low, and so that's going to cause even the average to be too high or too low. This would be like, if you're weighing apples at the grocery store and you stick your thumb on the scale every time. Well, all the masses are going to be too high, right? If you're reading the top of the meniscus instead of the bottom of the meniscus, all of your volumes are going to be too high. Those are systematic errors.